In a previous lesson, we found the number of positive divisors of small numbers, and we did this by listing the divisors. But what if we want to find the number of positive divisors of a large number, such as 14,000? In this lesson, we will examine a technique for this. Now, before we continue, I should tell you that it is not necessary to know why this technique works, but I'm going to show you anyway. For some students, the rationale behind this technique may be useful when tackling advanced integer properties questions. Okay, to begin, please recall something we learned in an earlier lesson. Now here we have the prime factorization of 720, which incidentally we can write as follows. Given the prime factorization of 720, we can draw several conclusions about the divisors of 720. For example, 4 is a divisor of 720, since 4 is equal to 2 times 2, and in the prime factorization of 720, we have 2 times 2. Similarly, 18 is a divisor of 720, since 18 equals 2 times 3 times 3, and in the prime factorization of 720, we have 2 times 3 times 3. Finally, 40 is a divisor of 720, since 40 equals 2 times 2 times 2 times 5, and this same product can be found in the prime factorization of 720. Now here comes a very important observation. Since the prime factorization of 720 consists solely of 2's, 3's, and 5's, the divisors of 720 must be in the form 2 to the power of a times 3 to the power of b times 5 to the power of c. Now since the prime factorization of 720 has 4 2's, a can be any number from 0 to 4. Since the prime factorization of 720 has 2 3's, b can equal 0, 1, or 2. And since the prime factorization of 720 has 1 5, c can be either 0 or 1. We're now going to use this information to determine the total number of positive divisors of 720. We will do this using some counting techniques you may have not seen before. We're going to build divisors in stages. Since all divisors will be in the form 2 to the power of a times 3 to the power of b times 5 to the power of c, our first stage will be to select a power of 2. Our next stage will be to select a power of 3, and our last stage will be to select a power of 5. Beginning with the first stage, the power of 2 can be 0, 1, 2, 3, or 4, so there are 5 ways to accomplish this stage. On to the next stage. The power of 3 can be 0, 1, or 2, so there are 3 ways to accomplish this stage. And finally, the power of 5 can be either 0 or 1, so there are 2 ways to accomplish this stage. Applying the fundamental counting principle, we multiply the number of ways to accomplish each stage to see that there are 30 ways to accomplish all 3 stages. So, 720 has 30 positive divisors. Now before we generalize these results, notice that the number of ways to select a power of 2 is 1 more than the exponent of 2 in the prime factorization of 720. Similarly, the number of ways to select a power of 3 is 1 more than the exponent of 3 in the prime factorization of 720. And finally, the number of ways to select a power of 5 is 1 more than the exponent of 5 in the prime factorization of 720, since the exponent here is 1. Okay, now let's generalize. If n is equal to p to the power of a times q to the power of b times r to the power of c and so on, where p, q, r, and so on are prime numbers, then the total number of positive divisors of n is equal to a plus 1 times b plus 1 times c plus 1 and so on. Notice that this technique requires us to find the prime factorization of the target number. So now let's apply this technique to find the number of positive divisors of 14,000. So first we will find the prime factorization of 14,000. And now to find the total number of positive divisors, we will take all of the exponents here and increase each of them by 1 before finding their product. When we evaluate this, we get 40, so 14,000 has 40 positive divisors. And that is how you calculate how many positive divisors a number has. If you wish to practice this technique, you can confirm the following.